So this is the third sum that we'll be solving on heat balance sheet. You can look at this sum a bit carefully. See, it is slightly different from the two previous sums that we have solved. Slightly different, not that much different. See, what are they telling us? That during a trial on a single cylinder two-stroke diesel engine. Okay, so this time it is a two-stroke engine, not a four-stroke engine. And it is again a single cylinder engine. So what are they telling us? Power supplied by electric motor for motoring at rated speed. See, again I will read power supplied by electric motor for motoring at rated speed. What does this mean? This means that they are using the motoring test. Okay, they are using the motoring test. See, motoring, power supplied by electric motor for motoring at rated speed. If you do not remember what is your dynamometer motoring test, okay, please go back to the dynamometer video and see what motoring test is. Motoring test is used to find the friction power of the engine, right? How does the motoring test work? We turn off the engine. First we keep the engine on, engine reaches a certain RPM, then we turn off the fuel supply to the engine and the engine is kept running using a motor. The amount of power that is required by the motor to run the engine is equal to the friction power of the engine. So basically what they are telling us through this, they are telling us that the friction power of the engine is how much? Friction power of the engine is 1.5 kilowatt. Okay, so this is the most important thing. This is what? This is your motoring test. They are telling us that a motor is required to keep the engine running at certain RPM. What is the RPM? 500 RPM. And what is the power that is required to keep the engine running at 500 RPM? 1.5 kilowatt. So what is this? This is the frictional power of the engine. Okay. So what have they given us? They have given us that it is a single cylinder engine, it is a two-stroke diesel engine. They have given us the frictional power, which is 1.5 kilowatt. They have given us the RPM. They have given us the net brake load, right? They have given us the diameter of the brake wheel, right? So they have directly given us the net brake load and they have given us the diameter of the brake wheel. They haven't given us any rope diameter or anything else. So again, we can say that this is what? This is a rope brake dynamometer in which we have what is 225 Newton. See, it is in Newton, so no need to multiply it by 9.81. They have given us the diameter of the brake wheel. That is what? They have given us the diameter of the drum. And they have assumed that the rope diameter is negligible. It is 0. So what will be the effective radius? Effective radius will be this diameter divided by 2, right? Then they have given us cooling water flow rate. What is the cooling water flow rate? 13.65 kg per minute. They are telling us that the cooling water temperature rises by 10 degrees Celsius. They have given us the fuel consumption rate 2 kg per hour, calorific value of fuel. They have given us the air fuel ratio. See, in the previous two sums, what they had given us? They had given us the fuel consumption rate and they had also given us the air consumption rate. But in this case, what they have done? They have given us the fuel consumption rate and they have given us the air fuel ratio. So using this you can find the air consumption rate also. Now, what is air fuel ratio? Air fuel ratio is mass flow rate of air divided by mass flow rate of fuel. So if you know the air fuel ratio and you know the mass flow rate of fuel, multiplying these two you will get mass flow rate of air. So what will be the mass flow rate of air? 32 into 2, which is 64 kg per hour. That will be the mass flow rate of air. Okay. So then they have given us the exhaust specific heat capacity, right? C of exhaust gases. They have given us exhaust gas temperature 345 degrees Celsius. They have given us ambient temperature. Ambient temperature means room temperature, which is what? 25 degrees Celsius. And they have given us stroke is equal to bore is equal to 0.03 meter. So this is a square engine. Remember, in a square engine, stroke is equal to bore, right? In an under square engine, bore is greater than stroke. In an underscore engine, stroke is greater than bore. In an over square engine, bore is greater than stroke. All our engines are generally either under square or square engines. Okay, over square engines are only used in ships, right? So this is what we have. And using all this, what are they asking us to find? They are asking us to find mechanical efficiency, indicated thermal efficiency, and brake thermal efficiency. So by now you should know that to find these efficiencies, we need to find brake power, indicated power, and thermal power. Okay, this is simple. But next thing what they are asking us to find brake specific fuel consumption. BSFC, what is the formula for BSFC? BSFC is mass flow rate of fuel divided by brake power. And mass flow rate of fuel should be in kg per hour and brake power should be in kilowatt. Do we know the mass flow rate of fuel? Yes, we know the mass flow rate of fuel 2 kg per hour. So if we just find the brake power, we will also be able to find brake specific fuel consumption. What is brake mean effective pressure? We only know two formulas for brake mean effective pressure, right? What are the two formulas that we know for brake mean effective pressure? Well, one formula is what? BMEP is equal to brake power developed in one cycle divided by the swept volume, right? This is one formula that we know. BMEP is what? Brake power developed in one cycle divided by swept volume. This is one formula that we know. And what is the other formula that we know? Arey, we know na, BP is equal to Planck upon 60 into number of cylinders, right? Planck upon 60 into number of cylinders. In this case, what is P? P is BMEP, right? P is BMEP. So, do we know BP? We can calculate brake power. Do we know the stroke length? Yes, we know the stroke length. Do we know the area? Yes, we know the bore pi by 4 d square. We can know the area. Do we know N? Yes, we know the RPM. Do we know K? Yes, it is a two-stroke engine, and two-stroke engine K is equal to 1. Do we know the number of cylinders? Yes, it is a single cylinder engine. So we know all the values except this P value. So we can use this formula after calculating BP, that is, we can use this formula and calculate the value of a brake mean effective pressure, right? So this is how all these values can be easily calculated. And the last thing that remains is your heat balance sheet. Now by now you should know what are the things that are required in a heat balance sheet. So what are the things? First of all, we need thermal power. Next we need brake power. Then we need the heat absorbed by the exhaust gases. Then we need the heat absorbed by the coolant. And then we need the unaccounted heat, right? These are the things that we need for our heat balance sheet. So all these things we are going to find. Okay. So I will go a bit fast because you should know these things by now, right? So you can always check the previous videos. In those previous videos, I have gone a bit slow than what I am going to do now. Okay. So let us see. This is just the given data. In the given data, what have I done? I have just written that it is frictional power. See, I explained to you that it is motoring test. So this is frictional power. What is the fuel consumption rate? They have given it in R, but because they have asked the heat balance sheet on minute basis, so what I did, I converted that R into minute. Okay. The air fuel ratio is given as 32:1. What is air consumption rate? Just now I told you mass flow rate of air divided by mass flow rate of fuel is equal to air fuel ratio, right? So mass flow rate of air is what? Air fuel ratio into mass flow rate of fuel. So that is what I have done. Mass flow rate of fuel, which is 2 kg per hour, into air fuel ratio, which is 32. So you get 64 kg per hour. Because everything has to be calculated in minutes, I just divided it by 60. So 1.067 kg per minute. What is the brake drum radius? Because they have ignored the thickness of the rope. The brake drum radius is brake drum diameter divided by 2, which is 50 centimeter, which is 0.5 meter. And angular velocity is what? 2 pi n upon 60. And what is n? N is the RPM. RPM is directly given to us as 500. So substituting that value, we can get the angular velocity also, 2 pi n upon 60. Okay. So substituting all these values inside this, we can solve these sums, right? So what is the first question that they have given? First thing that we have to find, the efficiencies. To find the three efficiencies, we need thermal power, brake power, and indicated power. So that is exactly what I have done over here. What is thermal power? You know only one formula for thermal power. What is that? Mass flow rate of fuel into calorific value. So that is exactly what I have done. First I have done it for R, it was 2 kg per hour, so I found it for R, divided it by 3600 and found it per second. Okay, so this is thermal power per second, right? Kilowatt means kilojoule per second, right? So that's it. What is brake power? Brake power you should know by now. Brake power is tau into omega, where tau is the braking torque and omega is the angular velocity. We have already found out the angular velocity, right? Angular velocity has already been found out over here. See over here, right? So that is what we have done. To find the brake torque, what do we have to do? Brake torque is what? Brake load into dynamometer radius. What is brake load? Brake load has been directly given to us by them only. See over here, they have directly given to us the brake load 225 Newton meters, right? And they have given us the brake radius. They have given us the brake diameter. So from brake diameter, we calculated the brake radius. So using these two values, we can calculate the brake torque. Brake torque is brake load into dynamometer radius. Substituting this value over here, substituting the angular velocity omega, we get the brake power. So what is the brake power? 5.89 kilowatt, right? So we have thermal power 23.89 kilowatt, we have brake power 5.89 kilowatt. Now how are we going to find the indicated power? See, this sum is that is why a bit different. In the previous sums, what was happening? They were giving us indicated mean effective pressure. In the previous two sums, they had given us indicated mean effective pressure. But in this case, what we have to do? See, in this case, they have given us the friction power, right? Because of this motoring test, they have given us the friction power. And you know, indicated power is what? Indicated power is brake power plus friction power, right? What do we know? Friction power is equal to indicated power minus brake power. So how can you calculate indicated power? Indicated power is friction power plus brake power. So that is exactly what we are doing in this sum. See, in this sum, we are saying that indicated power is equal to brake power plus friction power. We have the value of brake power. We know the value of friction power from our motoring test. Substituting them together, we get the indicated power. Okay, so this is what we have done. Now using the values of thermal power, brake power and indicated power, we can find the different efficiencies. Mechanical efficiency is BP upon IP, so we get that. Indicated thermal efficiency is IP upon TP, so we get that. And brake thermal efficiency is BP upon TP, so we get that, right? So we get these three efficiencies. What is remaining? We have to find brake specific fuel consumption. That is the next thing. Just now, just at the start of this lecture, I told you brake specific fuel consumption. What is the formula? Mass flow rate of fuel divided by brake power. And the mass flow rate of fuel should be in kg per hour and brake power should be in kilowatt. So this is directly given to us 2 kg per hour. We just found out brake power is 5.89. So substituting these two values, we get the direct value of brake specific fuel consumption, 0.34 kg per kilowatt hour. Okay. The next thing that they are asking us to find is brake mean effective pressure. I explained this to you. What is the two formulas that we know for brake mean effective pressure? Well, the first formula we know is what? BMEP is equal to brake power developed in one cycle. One cycle divided by the swept volume, right? We can use either this formula, but we do not know this value, right? It will be quite difficult, means not difficult, but it will be long to calculate this value, right? So rather we can do by this method also. It will give us the same answer, okay? There will not be any difference in the answer. But because this will become a bit tiresome, so to make it easier, we can use this formula. So this formula says BP is equal to Planck upon 60 into number of cylinders, where P is what? P is your brake mean effective pressure. So we know all the other values, right? So substituting all the other values and just keeping the value of P separate, we can find out the value of brake mean effective pressure. In this case, the value after substituting all these values, this is L, this is your stroke length. Here it is D. D is what? Your bore diameter. Bore diameter is also 0.03. It is given. This is what? This is your RPM. This is what? This is K. K is equal to 1. Why K is equal to 1? Because it is a two-stroke engine. This is the number of cylinders, right? Divided by 60. So P remains over here. 60 goes into the numerator and all these things go into the denominator, right? So doing all these things, we get in the end through calculation break mean effective pressure is equal to 333.33 bar. Okay, so that is your break mean effective pressure. So we have found out everything that we had set out to find. See, we have found all the things that they have asked us to find. We have found all the efficiencies, we found the BSFC, we found the BMP. The only thing that is remaining to find is the heat balance sheet, right? And just now I told you what are the things required to find the heat balance sheet. You have to remember this thing is very important. I am telling this again and again. This thing is extremely important. Keep it in mind. You have to find the thermal power, you have to find the brake power, you have to find the heat loss to exhaust gases, heat loss to coolant, and the unaccounted heat losses. Only after you find all of these things can you say that you can draw a heat balance sheet. So how are we going to start? We will start off with thermal power, but for thermal power we have already calculated thermal power per second, right? So just multiply it by 60 and you get the thermal power per minute. Second into minute, so multiply by 60. Same is the case for brake power. You know the brake power per second, multiply it by 60 and you get the brake power per minute. Okay, so we can substitute these two values. We can we can substitute these two values over here. So we know the thermal power and we know the brake power, right? Next we have to find out what is the heat loss to exhaust gases. By now you should know what is the heat loss to exhaust gases. MC delta T of exhaust gases. What is the mass flow rate of exhaust gases? Mass flow rate of exhaust gases is mass flow rate of fuel plus mass flow rate of air. So mass flow rate of fuel is given to us directly 2 kg per hour. Mass flow rate of air we calculated. How did we calculate mass flow rate of air? Mass flow rate of air is equal to mass flow rate of fuel into air fuel ratio, right? So that is mass flow rate of air. So that is the mass flow rate of our exhaust gases. It is in hour. I converted it into minutes because we have to draw the heat balance sheet on minute basis, right? What is the change in temperature of exhaust gases? Change in temperature of exhaust gases is temperature of exhaust gases minus room temperature, or in this case they are calling room temperature as ambient temperature. It is the same thing. So that is your delta T. So substituting the values M, C and delta T in Q, you get 1.1 into 1.006. They have given this value over here, and delta T is known to us. See, they have given C directly over here. See, they have given C directly. This is delta T, 345 minus 25. And using these two, you can find the mass flow rate of the exhaust gases. So using three things, we have directly found out what is the heat loss to exhaust gases. And we can substitute this value 354 over here. This is the heat loss to exhaust gases, right? Next thing we have to find out what is the heat loss to coolant. Again the same formula, MC delta T. But in case of this, we have to use this coolant, right? Coolant. So what is the mass flow rate of coolant? They have given the mass flow rate of coolant directly to us. See over here, they have given the mass flow rate of coolant directly to us. They have given the delta T of coolant directly to us. We only have to substitute the value of the specific heat capacity of coolant. What is the specific heat capacity of coolant? What are we using? Water. So what is the specific heat capacity of water? 4.18 kilojoule per kg Kelvin. So we will substitute that over here and we will get Q is equal to MC delta T. Mass flow rate of cooling water, specific heat capacity of water into change in temperature of water. So we get the amount of heat loss to coolant. We can substitute this amount of heat loss to coolant over here, right? So that is done. So we have found out this. We have found out this, we have found out this, we have found out this. We only have to find unaccounted heat losses. So what are unaccounted heat losses? Unaccounted heat losses is thermal power minus sum of all these three things. So what will it be? 1433.4 minus the addition of these three things. So that is what we have done over here. Thermal unaccounted heat losses is what? Thermal power minus summation of output heat energies. So 1433.4 minus the sum of these three. Brake power, heat loss to exhaust gases and heat loss to coolant. So unaccounted heat losses comes out to be 155.32 kilojoule per minute. Right? Substituting this value over here. we get our unaccounted heat losses. Now this, I think there is some mistake over here. I'm extremely sorry. I should write over here 1433.4. Here it should be 1433.4 and here it should be 1433.4. Okay. I'm extremely sorry. This is a mistake. This is how it should be, right? Please make the necessary changes in your presentation. This is how the final answer should be. Okay. Sorry, this is a mistake from my side. Because it should always be balanced, right? And that is the total amount of heat energy. See, thermal energy, total amount of heat energy. So that should be on both the sides. Okay. And the last step is what? Last step is we are just calculating these percentages, right? So we are calculating these percentages. How did we get 24.65? 24.65 is what? 353.4 divided by 1433.4. Okay. 1433. Here it should be 1433.4. Okay. So that is how we got 24.65. How did we get 24.70? 354.11. We substituted 354.11 divided by 1433.4. How did we get heat loss to coolant? To calculate heat loss to coolant, we put over here 570.57, right? And similarly for unaccounted heat losses 155.32. So this is how we get the heat balance sheet. Hopefully you have understood this. See, this was a slightly different question because the only main difference was they had given us the friction power, right? Rather than giving us the indicated mean effective pressure, they had given us the friction power. But it is important for you to understand that what exactly this is. To understand what this is, you need to see the dynamometer video, right? In the dynamometer video, I have explained to you how a motoring test works, right? Motoring test is used to find the friction power. So that is what has been done in this sum. So with this, see, this came in the CBCGS December 2019 exam. So with this, the third question ends. I will solve a couple of more questions. There will be question number 4. This I will solve in the next lecture. And then there is question number 5, which is by far the most difficult one that I have seen till now. But we will solve these both questions and be done with it. Okay. So in case of any doubts, you can always contact me and make the necessary changes over here. See, this should be 1433.4. Okay. And here also 1433.4. Okay. So thank you.